We're coming to the end of our 6 lectures on the growth of cosmic structures. And for the most part, we've focused on the construction of galaxies. And occasionally, we've looked at the way galaxies gather into groups and clusters. But in this lecture, I want to step right back and take in the really big scene. How do galaxies fill the volume of the universe? Are they spread about roughly uniformly, or randomly, or are there patterns? It's a bit like shifting from thinking about individual people and cities and asking, how do cities cover the Earth? For example, there are vast areas with none, the oceans, places where there are many, around a metropolis, and lines where there are many, coastlines and along major road systems. And surprisingly, this is roughly mirrored in the distribution of galaxies. There are regions with very few, voids, dense regions with thousands, clusters, and long filaments of galaxies, the galaxy web. So let's start close to home with a lovely movie that takes us on a trip from the Earth out to the Virgo cluster of galaxies, about 60 million light-years away. So our average speed will be 10 to the 13 times the speed of light. We begin by lifting up out of the Milky Way galaxy to see its full splendor. As we back away, 2 dwarf companions pass by on the left, the large and small Magellanic Clouds. Remember, big galaxies, like ours, typically have a few smaller ones in orbit about them. So as the Milky Way recedes, we pan around and the other 2 large galaxies that make up the local group swing into view. First M33, and behind it, the great Andromeda galaxy, M31. Notice these 3 big spiral galaxies are quite far apart, a necessary condition for them each to have a nice, thin spiral disk. Our trip now heads away from the local group. We pass M81 and M82. They're close enough that M82 has been disturbed and is now a starburst galaxy. We also pass M101 and the Whirlpool galaxy M51, whose little flyby companion has induced that lovely spiral pattern. Our view then wheels around and shows the wider distribution of galaxies. They seem gathered roughly along a line with a huge concentration on the left. That's the famous Virgo cluster of galaxies, and that's where we're heading. So our trip joins the line of galaxies to the right and then moves down along it towards the main cluster. This mirrors, at hugely amplified speed, the infall of these galaxies down onto the cluster to build it larger. The movie ends by heading straight for the dominant central galaxy, M87. And the last thing you notice is a faint blue jet on the left, a telltale signature of the 3 billion solar mass black hole that lives down at the galaxy's center. Now, it's all very well me showing a movie where we're zooming through millions of light years, but in reality, we're stuck here on Earth. How do we know what the 3-dimensional distribution of galaxies is? Actually, in principle, it's not that hard. Here's a picture of a 100-degree chunk of the night sky, with a Big Dipper for scale. All the foreground stars have been removed, and the image shows 2 million faint galaxies. Of course, some of those galaxies are near, and some are far. So to turn this 2-dimensional picture into a 3-dimensional one, we simply need to measure the distance to each galaxy. Now, to measure real distances to so many galaxies would be impossible, but fortunately, the Hubble law comes to our rescue. Remember, a galaxy's redshift is directly proportional to its distance. So an excellent first stab at getting distances to all those galaxies is to measure their redshifts. The greater the redshift, the further the galaxy. It's easy. So for the past 30 years, there's been huge effort to make redshift surveys. The pioneers of this were a group at the Harvard Smithsonian Center for Astrophysics. They used a 60-inch telescope at Mount Hopkins to take spectra, one by one, of over 2,000 galaxies. And ultimately, over a 10-year period in the late 1970s and 80s, they increased this number to over 18,000. But in the last 10 years, two teams have now increased that number to over 1 million measured galaxy redshifts. Not surprisingly, they've used bigger telescopes and also spectrographs that use optical fibers to record spectra of several hundred galaxies at one time. One team used the 150-inch Anglo-Australian telescope and its 400-fiber spectrograph to measure over 200,000 galaxy redshifts. And the other team used the Sloan Digital Sky Survey's 100-inch telescope and its 640-fiber spectrograph to measure 800,000 galaxy redshifts. These are huge projects that generate vast quantities of data and require large teams to manage. The Anglo-Australian team had 30 astronomers, and the US Sloan team has 150 astronomers. So what do these galaxy maps show us? Well, it's a little difficult to show the entire data sets, so instead cosmologists often take a moderately thin slice through the data that corresponds to an arc-like triangular wedge with us at the apex. So here's a typical wedge with about 100,000 galaxies, each plotted as a single dot. Notice we're at the apex, and the depth goes out to about 2 billion light-years. So our entire trip to the Virgo cluster took us no further than this little circle. This is a gargantuan map. It is 1/7 the way out to the 14 billion light-year visible limit to the universe. Here's our scale model from Lecture 2, where the visible universe spans the United States. The Milky Way is a 20-yard disk somewhere near the East Coast. The local group spans about half a mile. The Virgo cluster is 7 miles away. And these maps span 500 miles. It's a significant chunk of all there is to see. One might view our current situation like explorers around the time of Columbus. We've made a significant start at mapping what is a finite realm. As we'll see in Lecture 35, there are plans to measure, with somewhat less accuracy, the distances to 1 billion galaxies almost out to the visible limit. This is extraordinary. Within 400 years of Columbus, no part of the Earth's surface remains unphotographed. And within 100 years of today, maybe no part of the visible universe will remain unmapped. I'm not sure whether to feel awestruck at our capability or disappointed that nature yields to our instruments so easily. Probably a bit of both, actually. So back to the galaxy distribution. Notice how it has an interesting pattern. It's neither purely random nor purely regular. It has a mottled look. There are actually 3 types of features to look for. There are large regions with very few galaxies, called voids. Then there are long, narrow chains of galaxies, which can be sheets in 3 dimensions, and these border the voids. So the whole pattern looks like a 3-dimensional spider's web, hence the term the cosmic web. And where the chains intersect, there are rich clusters of galaxies, which can be 1,000 times denser than the voids. This whole pattern is really quite fascinating. Why does the universe look like this? What crafts this web-like structure? Well, by now you won't be surprised to hear that this kind of structure emerges when gravity acts over billions of years on the primordial roughness that emerged from the Big Bang. And the best way to demonstrate this is to shift our attention from the observational work to computer simulations that recreate the growth of large-scale structure. Now, unlike previous simulations I've shown you, which modelled one or a few galaxies, we now need to simulate regions several billion light-years across containing millions of galaxies. So these cosmological scale simulations are truly enormous in scope, and they push supercomputers to their limits. This graph shows the progress in computing power applied to cosmological simulations since 1970, when only 300 gravitationally interacting objects could be followed. And 2005, that number was 10 billion. That simulation was done by the Virgo Consortium, a group of about 16 primary scientists with about 60 collaborators from 5 countries. Here's a region similar in size to the survey I was just showing you. It's about 2 billion light-years across, and like them, it's a thin slice, about 60 million light-years thick. The full simulation followed the separate motion of 10 billion small samples of dark matter, each one weighing 1,000th of the mass of the Milky Way. They were initially spread out to match the lumpiness seen on the microwave background, and their simple, gravitationally induced motion was followed forward to today. In addition, gas and stars were included using the kind of semi-analytic methods I described in the last lecture. Ultimately then, 18 million dark matter halos formed, of which 2 million contain galaxies. In fact, here's the same region showing the distribution of galaxies. Let's get a better idea of the three-dimensional distribution of dark matter with this trip through the simulation. You can really sense the filaments made up of many halos of all sizes, with voids between and denser regions where they intersect. While we're zooming along here, I'll just mention that the supercomputer did 200 billion calculations per second for 28 days, marching through cosmic history at a rate of 6,000 years for every second of computer time. Okay, in this part of the trip, we're approaching a huge cluster with thousands of dark matter halos. You can also see the thick filaments that feed more halos down onto the cluster, constantly building its size. So let's now quickly check to see how well the simulation matches the real universe. Here's a comparison between the real galaxy surveys to the top left in blue and purple and similar-sized regions extracted from the simulation to the lower right in red. The overall appearance of walls, voids and clusters is remarkably similar, both visually and when you do a proper statistical analysis. So it really does seem that our picture of gravitational structure formation is at least approximately correct. Of course, I've just shown you the final patterns, but the simulation allows us to watch how the structure got that way. So let's look at that now. Here's the initial, almost smooth distribution of dark matter just 200 million years after the Big Bang, around the end of the Dark Age. You can already see areas of slightly higher and lower density, which I've marked with these shapes. Okay, let's start the movie. The redshift stretch factor is given at the top left, and as usual, cosmic expansion is not shown. We just follow the same region as time moves forwards. Notice how quickly matter moves away from the lower density regions to the higher density regions, enhancing the density contrast, so the web of filaments steadily grows more defined. As time passes, notice how the filaments near big clusters contain hundreds of galaxies that are falling down onto the cluster. One might even call these rivers of galaxies. Just like normal rivers, they're flowing downhill, where in this case, downwards is towards the large mass of the cluster. And just as lakes grow as rivers feed them, so clusters grow as these filaments feed them. Well, now the movie's over, let's just check that where our initial slightly higher and lower density regions, make sure that they indeed turned into the clusters and voids. And you can see they do. Perhaps the most bizarre aspect of all this is how such narrow filaments seem to magically appear. Why is that? Well, imagine a terrain of rolling hills. The peaks represent the highest density regions. These highest peaks collapse first, and because their tops are roughly symmetrical, their collapse in 3 dimensions is roughly spherical. But now think about a region between 2 adjacent peaks. It takes the form of a ridge. It's the path you would hike on a walk from peak to peak. When gravity acts on a line of higher density, it tends to collapse inwards to make, in 3 dimensions, a filament. So filaments form along lines between denser regions. Here's another movie of a somewhat smaller simulation, but it has the advantage of showing us the formation of structure in 3 dimensions by rotating the computational volume as it evolves. As before, the initial conditions are quite smooth, but as time passes, the clusters and filaments form. Now, at this point, I'd like to reintroduce the roughness spectrum from Lecture 17. Remember that all this complex structure can be represented as the sum of many, many waves, each of different wavelength and strength. It's a roughness spectrum. Here's the cosmic roughness spectrum for today's distribution of galaxies. On the left are large scales inferred from the microwave background, and on the right are smaller scales measured from the galaxy redshift surveys. It has 4 main features. It rises on the left, there is a peak, it falls on the right, and there are some small wiggles on the right. The shape means, moving from right to left, you can find ever larger structures up to a maximum of about 200 million light years. But beyond that, the universe is progressively smoother on larger scales. Remember, it's homogeneous on large scales. So what about those wiggles? What are they from? Well, if you think back to the Lecture 15 on Big Bang acoustics, those little wiggles are the faint remains of the acoustic harmonics in the young universe before the fog cleared, before 400,000 years. Here's the sound spectrum from the microwave background with its fundamental and harmonic peaks, and the odd compression harmonics survive through to today's roughness spectrum as those little wiggles. They're sufficiently weak that your eye can't see them as patterns in the galaxy maps, but a proper analysis shows that they're there as wiggles in the galaxy roughness spectrum. Their technical name is baryon acoustic oscillations. This is a truly wonderful notion. Primordial sound is still with us, writ large across the sky in the patterns of galaxies. Well, now let's come closer to home and add something that's been implicitly present all along: the flow of galaxies, including our own. Although we've seen simulations showing galaxies moving from voids to filaments to clusters, can we actually detect this movement? Can we see the galaxy flow pattern? The answer is yes, though it's not very easy. Here's the method. Let's think back to how galaxy maps are made using redshifts. With pure cosmic expansion, a galaxy's redshift should give us its distance exactly. That's just the Hubble law. But if the galaxy has an additional motion, because it's been pulled by nearby galaxies, then the measured redshift includes this additional part. Now, usually, in the maps, that's just thought of as an error on the distance. But now imagine you were able to measure the actual distance to the galaxy independently using one of the methods from Lecture 6, let's say the Tully-Fisher method. So now you know the part of the redshift linked to distance. So you can subtract it off the measured redshift, and bingo, the difference gives you the galaxy's gravitational motion. So combining redshift pi maps with accurate distances allows you to construct the galaxy flow pattern. Now let's be clear here, we are not talking about the global cosmic expansion, the Hubble flow as it's called. That's a given. We're talking about motion in addition to the Hubble flow that's arisen over time as galaxies pull on one another. Here's an analysis of the gravitational velocities in the local galactic neighbourhood, where local here means out to about 300 million light-years, about 10 times smaller than the pi maps I showed you earlier. It turns out that much of the action happens roughly within a giant plane called the supergalactic plane, so we won't miss too much if we just show this slice of the local universe on an XY graph, omitting the Z dimension. Here's the distribution of galaxies, with darker shading for more galaxies. We're at the centre in a relatively low-density region, with the huge Pisces-Perseus supercluster of galaxies to the right, and the Centaurus and Great Attractor superclusters to the left. Now here's the measured galaxy flow pattern, using little arrows to indicate the speed and direction of the flow at each point. And to keep the figures clean, I've showed a model fit to the data rather than the data itself. The results are quite impressive. Look how the flow always carries galaxies towards the denser regions and away from the voids, just as we expect. Galaxies are indeed falling downhill from voids to clusters. Actually, the speed at which they're falling is much higher than you would expect if they were only being pulled by the galaxies. As always, dark matter is dominating all of this gravitational motion, and the galaxies are really just along for the ride, being pulled by the dark matter. Okay, back to the Milky Way. Notice it's caught in a tug-of-war between those two huge collections of galaxies, the Pisces-Perseus supercluster on the right and the slightly closer Great Attractor on the left. The Great Attractor is winning the battle, hence its name, and the local region, including the Milky Way, is falling towards it at roughly 500 kilometers per second. Now, don't be confused here. We're still expanding away from the Great Attractor at 4,500 kilometers per second, but we would be expanding at 5,000 kilometers per second if it weren't there. It has slowed us down by 500 kilometers per second. So it's only relative to the Hubble flow that we are in fact falling at 500 kilometers per second. So let's now quickly zoom into this central square to look more closely at our own suburb before we back out to look at the even bigger scene. Here's the local group with the Milky Way and M31 sitting in a small filament that extends up to meet the much larger filament with the Virgo cluster at its centre. That's where our flight simulator movie took us at the beginning of this lecture. There also seems to be a void behind the Virgo cluster, and there are other smaller clusters to the right and below. The arrows show the flow pattern, which is once again away from the voids and towards the denser regions. And as you might expect, the local group and Milky Way galaxy are falling towards Virgo, moving at about 300 kilometers per second relative to the Hubble flow. And of course, this entire region is moving off to the left at 500 kilometers per second, falling towards the Great Attractor. So let's finally step back to look at the surrounding 800 million light-years, about the central fifth of those earlier pi maps. You can see the two previous regions with their concentrations of galaxies, but now you can see several much larger concentrations. The dense Coma cluster above, and the huge Shapley concentration, about 500 million light-years away, and containing tens of thousands of galaxies. Looking at the velocity field, it seems that although the Shapley cluster concentration strongly affects its local region, at 500 million light-years away, it's too far off to affect us directly. We primarily feel the pull of the Virgo cluster and the Great Attractor. Now let me end this lecture by looking at these large-scale flow patterns in a slightly different way. Remember how you can view all of structure formation as a hierarchy of collapse and merger. Early on, small high-density regions turn around and collapse. Later on, larger high-density regions do the same thing, expand, slow, turn around, and collapse. And they include many of those earlier, smaller objects in their collapse. Well, these large-scale flow patterns that we've just been looking at are really just the latest stage in this game. We have huge regions that are just beginning to slow their expansion, pulled back by their higher density. Now, here is an interesting question. Will they ever finally halt, turn around, and collapse to form super-duper clusters of galaxies? The answer is no, they won't. And here's why. Dark energy has begun to affect cosmic expansion. It's driving an acceleration, and this significantly affects the future growth of structures. Basically, the growth is shut down and frozen in its current pattern. This figure shows a simulation of a billion light-year region that is designed to match our own neighborhood. So we're at the center, here's the Virgo cluster, and you can see the same galaxy patterns I've just been showing you. Now let's jump 14 billion years into the future. That billion light-year circle now appears smaller because, as usual, we're not showing the expansion. Okay, let's jump another 14 billion years into the future. Notice how the structure just isn't changing. It's been frozen by the accelerating expansion. Of course, by this time, the Milky Way and Andromeda merged long since, but we never fell into Virgo, and Virgo never grew much larger. Now let's jump 100 billion years in the future. The billion light-year circle is now a dot at the center, and a new red dashed circle has appeared. That's the distance at which the expansion speed is the speed of light. It's called an event horizon. Now, as you might imagine, you can't see anything outside this circle because the light never gets to you. Ultimately, even the Virgo cluster will be outside the event horizon, and the universe will appear empty except for our own local ball of stars, what was once the local group. Let me very briefly review the main points of this lecture. Rather than focus on individual galaxies, we stepped back and looked at the overall pattern of their distribution. This pattern has become visible using huge surveys of over 1 million galaxy redshifts, which span several billion light-years. We see a web-like pattern with voids, filaments, sheets, and clusters. All these features are nicely reproduced using giant computer simulations that follow the motion of literally billions of objects that represent dark matter, starting from the slight roughness in the early universe. Using these simulations, we can see how the patterns steadily become clearer as gravity pulls galaxies from lower density regions to higher density regions. And we can even see the remains of the acoustic harmonics left over from the sound waves in the million-year-old universe. We also saw how combining distance measurements with redshift surveys allows us to map out the galaxy flow patterns superimposed on the Hubble expansion. It turns out, locally, we're falling towards the Virgo cluster, but we and the Virgo cluster are both falling towards the Great Attractor. Finally, we learned that this ongoing growth of structure will soon shut down as the accelerating expansion caused by dark energy freezes the pattern of galaxies more or less in its current form. Well, our lecture course is a little over halfway through. So I hope you're ready for a change of topic. We have several wonderful themes coming up, starting next lecture with the story of how all the atoms that make up our world, including you and me, were first made.